In this video 6, I will speak a little bit about complexity, and then about quantification over possibly higher order Boolean function, as well as simple Boolean functions. This is also supported. By that, we will see how we can increase complexity, and by that also expressiveness. So there is a paper by Kozen about complexity of the theory of Boolean algebra, and he showed that the satisfiability of a formula in the language of Boolean algebra for infinite Boolean algebras, yes, is the following complexity class. STA stands for space-time alternations. So we are talking about alternating Turing machine. It is whatever alternating Turing machine can do with unlimited space. C to the n time, we will see in a moment what this C is, and n alternations. And here we take the union over all real C greater than 0. So the satisfiability problem of the language of the theory of the language of Boolean algebra is complete for this complexity class. So roughly speaking, you can say that it is anything that alternating Turing machine can do in exponential time and linear alternations. This is contained in X space. And obviously, it is also contained in non-deterministic exponential time. For finite Boolean algebras, this is very simply p-space complete by direct reduction. Maybe it's not even reduction, maybe it's directly the very thing itself of QBF. Okay, now for quantification over Boolean functions, suppose we have exists a Boolean function of, let's say, 2 variables. So let's write it, I don't know, like exist f(x) of y, such that, and now you can do whatever you like. You can do, let's say, f, you can also compose function x, y, equal f, y, f, y, x, I don't know, something like this. We will show how to eliminate quantification over Boolean functions to quantification over Boolean algebra elements. Well, and that's straightforward. So any Boolean function of n variables can be written in internormal form, and that's only one way to do it. Of course, all similar ways are valid. You simply write it like this. So all you have to do is to quantify over the elements which are the values of f on 0, 1. And then you can see very trivially how this single quantifier is really, here we have 2 variables, so it can be written as 4 first-order quantifiers. Now, this is maybe a little too much to always have direct exponential explosion. So what you can do is you can convert single n variable, or let's say let's call it arity, n function quantifier into 2 n-1 arity function quantifiers. And when you reach arity 0, then you quantify over a standard Boolean algebra elements. This is simply Boole's decomposition. F, x, and x, so we distinguish one variables equals f, g, x plus x prime, hx. So you can go variable by variable and reduce the arity, and then you get more opportunities to simplify your formula, so you don't always have to pay the full exponential price like in here. And of course, you don't have to follow only Boole's decomposition. You can have a algebraic normal form, which is like this. There is also a generalization of algebraic normal form that gives you the composition of not into two functions, but of n functions of decreasing arity n minus 1, one is arity n minus 2, and so on until 0. The case for higher order Boolean functions is completely analogous. There is nothing to say here. It's completely analogous. And the same for simple Boolean functions. Now, quantification of the simple Boolean functions is especially interesting because which gives the theory of Boolean algebras of cardinalities 2 to the 2 to the n, because that's the number of simple Boolean functions. So those Boolean algebras are particularly interesting. They stand out of the rest of the finite Boolean algebras, because when you write them as simple Boolean functions, you can do more stuff, namely you can compose. Also operations that are not available to you in other Boolean algebras. Maybe it's a good place to mention something that maybe I should have mentioned before. All countable atomless Boolean algebras are isomorphic. Let's see some manifestations of those. So each BA element is a finite union of left closed, right open intervals over the rational numbers. This is a countable atomless Boolean algebra. The one that I prefer to work with when I try to study the general properties of countable atomless Boolean algebras is the BA of SBFs, the Boolean algebra of simple Boolean functions with unboundedly many variables. So each function refers only to finitely many variables, but you have an infinite supply of how many variables you want to use. By Stone duality, this corresponds to the topological space, which is the Cantor set, the middle thirds thing. And maybe I will also mention that all atomless, not necessarily countable, Boolean algebras are elementarily equivalent, which is, in other words, to say that every sentence in the first order theory of Boolean algebra is either true in all atomless Boolean algebras, or it is false in all atomless Boolean algebras. This was proved by Tarski in a much more general framework, where Tarski was able to classify Boolean algebras according to what he calls invariants. So to each Boolean algebra, he attaches 3 numbers. And if 2 Boolean algebras have those same 3 numbers, then they are elementarily equivalent. All right, now, you know from a finite model theory, and if you don't know, then it's not gonna harm the progress of the material, that model checking finite models with a second order logic formula captures the polynomial hierarchy. The notion of capturing in the field of descriptive complexity is different than the notion of completeness. So one way to say it is, to any problem in the polynomial hierarchy, there is a second order logic formula such that if you encode the input to this problem as a finite model, then this decision problem can be done with a model checking against that formula. Now, as far as I know, no remotely good algorithms exist. Algorithms that take a formula in second order logic and a finite model and tells whether the model models the formula. It is easy to give an algorithm that is always exponential, that is always of horrendous complexity, but my definition of good algorithm, what do I mean by a good algorithm? Is an algorithm that runs fast on many easy instances. So it has a lot of opportunity to return answer quickly. Now, I will show you why the above quantifier elimination method for quantification of Boolean functions, when we do it step by step and not paying the full exponential price immediately, why it is a good algorithm for this very problem of finite model checking of second order logic. Well, that's really very simple. So if the model is of size n, the domain in the model, then you need, of course, log n bits for each element. Then you can convert the model to one with domain of size 2 by increasing all arities times log n. Similarly, you modify the formula. Yes, you increase the arities and you make the formula suitable for working over domain of size 2. Any relation, any k Ari relation is nothing but a simple Boolean function with k log n variables. All is left to be done is to encode the structure as a formula, and the model as a formula, conjunct with the input formula, and check for satisfiability. And now I will show you how we can extend the theory of Boolean algebra to make it able to solve by reduction, yes. So you can reduce in polynomial time any problem in the complexity class elementary. And because there is no complete problem in elementary, so this should be complete for a certain non-elementary complexity class. So how to do this? So first we appeal to finite model theory, or descriptive complexity. That's basically two names to the same field. So for finite model theory, we know that higher order logic captures the complexity class elementary. Now, just like I explained how to solve second order logic, how to model check second order formulas on finite models, if you have higher order formulas, well, instead of simple Boolean functions, you simply use a higher order simple Boolean functions, and that's it. So we can see how to solve any problem that is solved by any tower of exponentials can be reduced in polynomial time to a decision procedure in the theory of Boolean algebra extended with quantification over possibly higher order simple Boolean functions.